is made like this in order to made easy in order for a lot of people to join and use. Okay, so 5 minutes. I'm gonna share my screen now and start the lecture. So the lecture today will talk about integrated assessment models, which is pretty much what the people from IASA does. They develop integrated assessment model, which is message. And the lecture today will talk about the installation of Anaconda, which is the Python editor. We'll talk about sustainable development and sustainable development goals, shared social pathways, integrated assessment models, needs, and the models themselves. We'll go more in details on IASA, on climate models, and then talk a little bit about energy storage in future integrated assessment models, which is what's going on today with message. Hello, Lara.
Hello, Julian.
I stopped sharing. Sorry. Hello. Okay, so installing Anaconda. This is a very important step for today. So this could take some time. It's good if you guys start installing now, because during the lecture, if you have any question on how to install, I can answer the question while in the end of the lecture. So uh guys, can you please go into this website, and in the very bottom of the website, hello Flavio. I'm not sure if all of you are on your desktop now. There's no there's no Anaconda for mobile, so if you're on your desktop, please do this now. If you're not on your desktop, if you're on your phone, please do it later, which is to install Anaconda so that all of you can learn how to program in Python and how to design energy models and long-term energy models. Um, so I'm sharing in your chat box. It's anaconda.com, the website, and please put the link in your browser, and then the download packages are on the bottom where it writes Anaconda installers. Depending on your operational system in Windows, Mac, or Linux, you can install the Anaconda that runs in your PC. So it might take some time to download. So please just click in whichever these you have to download. It's going to download in your PC, and then you can install after it's downloaded. I'll remind you in the end of the lecture. So can everyone do this, please? Can you say yes, or can you ask questions in the chat box if you have? My voice is breaking. Thanks, Marcus. Did it improve now, Marcus, or do you think is the phone my phone or is my internet? I'm going to remove some of the. Thanks. Um, I don't think I will be able to improve my internet though. Is that only Marcus' problem? Everyone can hear me well, or just Marcus? Maybe Marcus is not.
I'm hearing you very well.
Okay, thanks, Natalia. Okay, Marcus, apparently it's your internet because people can hear me. So yeah, just make sure you have good connection. Thank you. Thank you for sharing. Thanks for telling me. Okay, guys. So let's install Anaconda and then follow these steps afterwards. I'm gonna share with you. It might take some time for you to get there. Uh, so they recommend you to install the latest version, which is 3.8. Maybe it's 3.9, but it's okay. This is a following step that Natalia will go with you through in next lecture to use the Anaconda prompts, make it easier to install. Right, so I'm gonna remove my headphones because I think it's better. The microphone is better with the screen. Sustainable development. This is the main goal that we people use integrated assessment models. They can have a goal for example, destroying another country. They can have goals of developing their own industry, becoming increasing their GDPs, several goals that a country might have in order to run integrated assessment models. But usually, most in the literature, most countries, they focus on having sustainable development. Sustainable development has the interest, the objective of taking into account economic aspect, social aspect, and environmental aspect in the decision, in the development of energy plans for developing a country. The idea, if the three of these aspects are taken into account, the development will be a sustainable development. This is the main objective. And looking at particularly integrated assessment models, they have the main objective to focus on the same goal, which used to be the Millennial Development Goals, which is organized by the United Nations and the Global Environmental Facility, the World Bank. So all institutions linked with the US and how they think that the world should develop. Of course, China is also included. Every country which takes part of the UN has the goal of having these Millennial Development Goals, which is to help other countries which are very poor to eradicate extreme poverty, to achieve universal primary education, to promote gender equality and empower women, reduce child mortality, improve maternal health, combat HIV, AIDS, malaria, and other diseases, ensure environmental sustainability, and develop a global partnership for development. So this was until 2012, 2013. They used these goals in order to develop parts of sustainable development, particularly in poor regions, poor locations. And then now the main goal changed. Now they have 17 goals, which are now called the Sustainable Development Goals, which has received a lot of focus for example, people that are developing these integrated assessment models, because integrated assessment models has the objective of matching several aspects of development into the model. It's not only, for example, energy. It's not only, for example, um, fuel production. It's not only economic development. So what happens? What am I telling this is because if you are an academic and you're going to write a paper about integrated assessment models, 80, 70% of the papers they at least mention these sustainable development goals. They might focus on one or two or three of them, and this is just a way for people of the broader academic literature, science, to understand what you're talking about and why you're focused, because they need to talk in the same language so that people is clear to everyone what you're trying to do. So these 17 sustainable development goals also developed by the United Nations, World Bank, and several international institutes. For example, YASA participated on developing this. So they have the objective to have no poverty, zero hunger. They probably copied from the previous presidents, Fome Zero, so it's zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy, decent work and economic growth. Number seven, industry and innovation and infrastructure, reduced inequalities, sustainable cities and communities. 12, responsible consumptions and production. 13, climate action. 14, life below water. 15, life on land. 16, peace and justice and strong institutions. And 17, partnerships for the goals. So it's a partnership to reach these goals. So these goals, of course, are if you want to publish a paper, if you, for example, are a minister from a government, maybe the goals are not to reduce poverty, to increase hunger. Maybe the goals are to heal people, for example, their own people in the country. But of course, this changes in each country has a different goal. So these are just generic goals so that everyone knows what they're talking about. So it's important to show this. The goals that message and IASA tries to focus more is on water, um, energy, clean energy, and economic growth, infrastructure, sustainable cities and communities. So these production and consumption, climate action, life below water, and life on the land are the most important for these integrated assessment models, because the other ones are a little bit more complicated and the policies are more difficult to implement, to create equations to describe the other goals. So they're more challenging, and these are the ones that are mostly focused. So another important way of looking on how humans will develop in the future, the the research community, the UN, YASA, and these institutions, they created the shared socioeconomic pathways, which are also called SSPs. So if you're in a conference talking about integrated assessment models, they'll talk about SSPs, SSPs, SSP, SSP all the time. So if you want to know about integrated assessment models, you should know SSPs, which is also a way in order for everyone to understand what you're trying to reach, what your model trying to develop easily, so everyone understands what you're talking about. So this is a graph showing, for example, five SSPs, which are the most important ones, and how they fit in these X and Y axis. So the axis shows that the socioeconomic challenges for adaptation. So these two, they have to spend a lot of money and focus on adaptation to climate change. And these two, they have to focus a lot of money into mitigation measures. So mitigation measures in order to avoid that you have climate change. Mitigation measures for reducing climate change impacts are, for example, reduce CO2 emissions, stop deforestation, so reduce the amount of CO2 in the atmosphere, reduce the heat in the world. For example, allowing the Arctic Ocean to continue to be frozen. If you somehow remove the layer of ice on the Arctic, you're going to heat up the Arctic. So mitigation solutions. And adaptation is after you have climate change, you have global warming, you have to adapt. For example, creating barriers in order to stop the sea rising. The sea is not going to stop rising, but it's going to avoid flooding a city. So barriers to stop flooding cities. Um, for example, air conditionings. Invest in technologies that operate well with high temperatures, flood controls. There will be a lot of floods in the future. So have solutions for flood controls, having solutions to mitigate, to adapt against fires. So wildfires will increase in the future. So these are the ones. So the first one, which is the most optimal, you don't have to spend money on adaptation or mitigation, is if society somehow decides that they should go green, they should behave sustainably. Every country in the world, they agree and they collaborate in order to be sustainable. So, for example, people start eating less meat, people drive less cars, they start working from home, there is less international trade, so it's sustainable development. On the other hand, for example, this SSP 4 is adaptation challenges dominate. So the idea is that you have a lot of inequality. For example, you have a lot of very rich people, you have very poor people. So the rich people, they manage to solve their problems. They have electric cars, they have renewable technologies, but there is a lot of people that still don't have money. They might not even be able to buy gasoline, to buy fossil fuels in order to have a good quality of life. So the mitigation is okay because CO2 emissions are low, but you have a lot of problems with adaptation because constantly the people try to survive and they'll try to survive in a manner that might not be the most effective and sustainable. And then you have problems with adaptation. The SSP 5 is the case that, for example, we continued life burning a lot of fuels, and everyone can burn fuels, and we emit CO2, and energy is cheap, and then we don't have problems. But of course, the mitigation side is going to be an issue because you have a lot of CO2 emitted to the atmosphere. You might not have so much problem with adaptation because you spend a lot of energy from fossil fuels in order to create several things to solve your problem. You create barriers, create a lot of things. So adaptation is easy because you have cheap energy. With cheap energy, you can do almost anything. And the SSP3, you have rivalry. Regional rivalry is you have wars, so people are not collaborating, and then you have a lot of CO2 emissions because people are killing each other and they don't care about not emitting CO2. And then, of course, also you have problems with adaptation because during a war, you can adapt with climate change. And then you have the middle of the road, which is not one or the other, is in the middle, is a bit of everything, which is more or less what we're having today. SSP2 is the most accepted and most used social economic pathway. Not sure if I managed to express myself clearly. If you guys have some questions about this, please ask. This is a bit more detailed. I'm not going to go through so much in detail on this, but I'm going to leave this slide here for you guys to have a more look on the assumptions for each of the SSPs. And the main objective, for example, in integrated assessment models is to see in each SSPs how are people going to emit CO2, how the CO2 concentration in the atmosphere will increase, For example, in 2020, we are somewhere around 420, 410 to 420 parts per million of CO2 in the atmosphere, and this is expected to vary. And depending if we have a war, this is SSP 3. If we're just burning ourselves away, this is SSP 8. CO2 emissions is going to increase rapidly. You have the middle of the way, SSP 2. That's how the CO2 emissions are expected to rise. And then you have the more sustainable alternatives for SSP 1, which are these. And for example, SSP 1 in 2030 to peak CO2 emissions, 2040, 2030, I think is very challenging. It's probably going to be something like the yellow, or between the yellow and the red, even given the fact that we have a lot of Tesla, and Elon Musk is saving the world, making a lot of money with this, but I don't think it's going to be enough. So we might probably emit CO2 emissions with this concentration, with this amount, reach this concentration, which is going to heat up the world. We're going to have sea level rise and all that. Right. So how integrated assessment models work? I created this slide just to give you an idea. You have a country has, or the world has, natural resources, wind, solar, water resources, oil, land, animals, forest resources, precious metals, natural gas, and also has financial resources, technology, human resources, and demand. And it also needs to avoid as much as possible environmental impacts and social impacts. So the thing is that, for example, if you build a lot of solar power, solar energy, yes, you have some impact in the social impact. It's going to cost you a reasonable amount of money, but maybe it's not going to fulfill all the demands for people for energy, because they're not going to consume energy just during the day when it's sunny. So they also need land in order to produce food, and in order to have a very prosperous economy, and then they have good jobs and they compete better with other countries. And whichever pathway you decide, whichever way you decide in order to develop your country, they will have different impacts and different consequences on money, on your economy, on the people that live there, on the environment. So this is the needs of integrated assessment models. You just need to take into account all the aspects in order to come up with the best scenario. For example, natural resources, technologies, demand. Demand is usually the most important one. If you don't have demand, there is no need for any of these. Human resources, financial resources, economy, environmental social impacts again, sorry. Climate change. Climate change is also a important issue. So there are several integrated assessment models doing this. For example, Message. I work on Message in IASA that is developing one integrated assessment models. There is Minds, Image, GCAM, uh, I, IAM, several ones here showed in this graph. Some of them use optimization models. For example, um linear programming, several other optimization methodologies. Some of them use recursive recursive dynamics, which is literally you create a scenario, you click a button, it's like an Excel spreadsheet which calculates the cost, calculates the emissions. So it's not an optimization model, so it has less resources, but it might be what you want because, for example, you have when you make decisions, when you create policies, it's kind of a deterministic science. You create a new scenario, you create a new policy, you want to see how your policy works. You have your your world there functioning. You create new power plants here and there, and then you want to know how uh, how this model will give results. How much it's going to cost? How many CO2 emissions? The other option is to for you to give allow the computer to select what's the best solution for you, what's the most optimal solution. There are two different type of models. There is general equilibrium, which looks in the world as a whole. For example, for partial equilibrium, you have equilibrium for each of of the countries. Then you have an equilibrium after you have partial equilibrium. And looking at different models in Brazil, so there are people developing these models in Brazil. We have the people from Copy, UFRJ, which is led by Roberto Scheffer. There are several people working on these projects. They started with Message Brazil. Basically, there was some collaboration in Message. Some of the students from Roberto Scheffer went to IASA and they learned how to use Message, and they decided to create a Message Model Brazil, which is actually currently going on in Promec with Natalia. Natalia is developing a Message Brazil now. We took Message Brazil that we have from IASA, and we took a new model representations with storage, which Bernam is leading this, and he's going to actually talk to you about this project and this development. But this Message Brazil was around 15 years ago, and then the researcher came back to Brazil. He developed coffee. He developed blues. He developed tea. So very nice names, but literally is the Message Model Brazil with a different name. They might have changed a little bit of the mathematical modeling representation, the optimization model. I don't think they did so much. I think they just improved the message model. They have they have added some characteristics like impact on land. So if you want to produce a lot of biofuels or biomass, how much land you would need, and how much land you will need will tell you, well, you increase deforestation, we'll have CO2 emissions and all that. So they created a message model focused in Brazil. There's PSR, PSR, which is one of the main energy consultants company in Brazil, probably the main energy consultant company in Brazil. Nowadays, probably more important than CPEL, which is from Eletrobras. And they have their own model called SDDP. It's also an optimization model. It's not used in Brazil, but they sell this model for other countries. So uh, they provide consultancy in different countries. The one used in Brazil is Matriz, the name of the model. It's not open source. We can't download. We don't have the documentation. It's closed, and it's what Brazil uses to plan its energy system. And it was developed by CEPEL. Nowadays, it's operated and atualizado, updated by EPE, Energy, Empresa de Planejamento Energético, which is in Rio de Janeiro, and they're the ones that plan the energy sector for the next 20, 10, 15, 20, 50 years. So Natalia was very nice to share me this website, which shows some of the main um, integrated assessment models. And here you can look at the different goals, the different names, the different solution concept, horizon methods, anticipation, temporal dimensions, spatial dimensions, policies that you can add to the model. and how the model works, literally. So you can compare different models with this tool. It's very useful. I'm not going to go through all the all the comparisons in detail, but yes, I'm gonna share with you this if you're particularly going to work, write your thesis, write a paper on integrated assessment models. There is a lot of work going on the topic. Just sharing some information you have, for example, coffee image, message, pose, and time. Uh, so there are some descriptions here. You have the name of different models. Message Global is the one that's is under implementation nowadays. I work with Message Global. You have solution concept, general equilibrium, partial equilibrium, partial equilibrium, solution methods, linear programming, simulation. So simulation is the one that you create your world and then it calculates afterwards. Optimization, it creates the scenarios automatically, but message is linear programming also. But of course, there are several other links and other methods linked to message, so it's difficult. It's not 100% a linear program tool. So Pose is a simulator and recursive simulator, and time TIAM is a linear program, linear optimization. The temporal resolution varies with the model that you want to create. Really, usually a message varies every 10 years, but this is not fixed. Um, you can vary the time, how many time dimensions you have. You can make scenarios every 10 years, every 5 years, every year, every 50 years. It depends how much in the future you want to look. Spatial dimensions, coffee has 18 regions, image 26, message 11, pose 66, TM has 16 regions. Energy technology choice, linear choice, logit choice model. This is a message has linear choice, pose has logit choice model. So if you, for example, did engineering, you probably had a lecture called um, programação operacional, something like this. Programação operacional. This lecture, you learn linear programming, you learn several other optimization models. So these are these optimization models that we're looking here, which you learn in operação, programação operacional. There was one attempt in the beginning on 1973, 1978 for creating a global change assessment model, which would take into consideration all the other efforts in order to build a ultimate integration assessment models, and you would try to combine all the existing ones. It didn't really work very well. It was very complex. Every person has a different approach to solve a problem. You can't really always combine different approaches. So this is the global change assessment model, combined human Earth systems with geophysical energy Earth systems. It's very complex, very big. It's not under development anymore, but it was a big attempt to create one Uber overall integrated assessment model. But nowadays, what's happening is that each research institution that worked on this worked on their own tools, and of course they use their own tools for project development and for country analysis. For example, Message has maybe 5 or 6 countries that use Message in order to plan their energy sector in the future. For example, India, Pakistan, um, some countries in Africa. I think there were some countries in Europe that used at some point, but they stopped. But it's still actually being used by country regulators. So here is the framework of message. Message is mostly focused on the energy sector, water demand, but there are several other tools which have been developed in order to increase the the reach and the amount of aspects included in the optimization model of message. For example, there is Globiome. I'm gonna go through more in more detail in the next slide. But also there are several other, for example, Nest is a tool focused on water, energy, food, land and food. Nexus, which uses message. So there are several tools which also come out from message, which have different names, but they're basically message models. And message is the integrated assessment model developed in EASA, which I have been working on. So looking at each of these aspects in this slide, you have Globiome is linear programming. It has the main objective to see how much land each country has, to see if you can, for example, produce biomass and not impact the cost of food. For example, if you have enough water to produce biomass, they have transport module because transport sector is represented in message. So how people choose if they're gonna go to work by train, by car, by motorcycle, by bike, walking. So you have a model here which is a discrete choice logit model. You have this this section which is access, which is for very poor countries. How they're going to cook their food? Are they going to use wood? Are they going to use uh, gas, biogas? Are they going to use coal? This coal can impact their health, for example. And then they have a district model in order to make to estimate their decisions according to how much money they have, how much money the country can supply to them. Macro is a economic representation, macroeconomic representation is non-linear programming, is the methodology it's used. Gains is a tool for estimating the impact on air pollution. So, for example, if you have several power plants, one close to each other, coal power plants, the impact on health, on air quality will detriment, will reduce considerably. So, this GAMS estimates the impact of energy generation on air quality. You have Magic. Magic takes the data from message, the CO2 data from message, and tries to estimate what's the impact on the climate, how much is the world going to warm up, how much sea levels are going to increase. And then you have the shared socio-economic pathways, which is input, data input for message showing how much people will demand energy, how much food is going to be demanded, how much area is required, for example, for plantation, what's the size of the population of the country. Population will increase, will reduce. This is dictated by the shared socio-economic pathways. Yeah, so there is a lot of work, several thousands of papers talking about integrated assessment model. I'm just going to scratch the surface here. I'm going to give a little bit more detail on these. For example, gains. The idea is to see how much sulfates, NOx on the air, carbon monoxide. For example, if you are working in a factory, this can impact people's health, and it's mostly focused on air quality, games. So macro, this is also a representation of macro, which is the economic side of message. So, for example, if you invest a lot of money in the energy sector, you're going to have a feedback loop, and then the economy is going to grow, and then you need to invest even more. And how much this interaction works is very important know to know if your economy is going to increase, how much energy you need, so how much supply and demand. So this is important for supply and demand. which in case message is the supply part, and macro dictates the demand for electricity. There's GloBiome also, as I mentioned. It looks how much food is delivered, how much land you have, and then it's a linear optimization model. It tries to estimate how much energy, land, and water is left for you to produce biomass, biofuels, and other things from you're interested to do. Industry also, for example, you need wood to produce, you need raw materials, you need natural resources in order to produce to increase economy. Then you need to know how much area you have, the age of the trees, how much resources you have. So this is more focused on the land and water resources of the message model. Magic looks into the climate change impacts. So then the energy system model, which is message, gives up these results, which is CO2 emissions, uh, sulfates, and then it gets into message and then calculates global mean temperature rises, so how much temperature will increase, sea level change. I'm not sure if they look into flooding risks, fire risks. It shows here they doesn't, but there are several other climate models which does, and they estimate. I'm gonna talk a little bit about climate models just for you to get a bit familiar with the terms and the concepts behind climate models. The main concepts that are used in integrated assessment models, because when you're developing integrated assessment models, the idea is to reduce CO2 emissions. But in order for you to know, for example, in 50 years, what's the temperature, how much rain you're going to have, how much hydropower you're going to produce, how much wind you're going to produce, how much solar power you're going to produce, you need to have very, very good climate models in order to dictate if it makes sense for you to invest today in solar power. For example, maybe you invest in solar power and in that region where you live is going to increase 3 or 4 degrees Celsius and the radiation will reduce. Maybe, and then it's not going to be viable. So in 10 years, you're going to have a solar power plant which is not going to produce so much energy as you expected. The same for hydropower. So hydropower has a huge impact with climate change. Climate change has a huge impact on hydropower generation. So, for example, you want to build a dam and generate a lot of electricity. Maybe in 10 years, in 20 years, you will be generating half of the electricity because the rain patterns reduced. So climate change and you have less rain, less water to produce hydropower. It's very important to have these climate models particularly if you're looking at renewable energies to see if you will generate the amount of energy that you intend to. So there are also several climate models. So climate model is something extremely different to integrated assessment models, but is one very important uh, input data. Is a very important source for input data for temperature, irradiation, wind, precipitation, and all these parameters. It's also important to know the type of scenarios that are mostly used. So, for example, if you're running a scenario in the future, you have these representative concentration pathways, so RSP, RCPs. So the RCPs, representative concentration pathways, they show pretty much how much CO2 emissions will increase in the future. For example, if you're doing a regional model, and your model is not going to dictate how much CO2 emission is going to be emitted, but the CO2 emissions that there is in the atmosphere will impact your decisions because you will have a different climate in the future. So this RCP 8.5 is the worst. So it shows that everyone's emitting a lot of CO2. And then you have the RCP 6.0, which is probably what's will gonna happen in the future. Then we have the RCP 4.5, which is a little bit more optimistic, and then the RCP 2.6, which is very optimistic that in 2040 we will have CO2 emissions starting to reduce. It's very difficult. Sorry, not CO2 emissions, it's CO2 concentration in the atmosphere. In order to reduce CO2 concentration, there are some options. Maybe the ocean is going to eventually absorb all the excess CO2 in the atmosphere. Maybe you have to do carbon capture storage. So you have to, for example, burn wood, which is absorbs CO2 from the atmosphere, and then you inject it in a well, and then you remove from the atmosphere. So this reduces the concentration of CO2, which is very challenging, very expensive, and it's very difficult that in the future this is going to be a reality. But maybe, if people are really concerned and spend a lot of money to reduce CO2 emissions, it could be done. So climate models have developed substantially from the past. In the past, it was only taking into account the atmosphere and land surface, and then several other aspects is included. And nowadays, we have very, very good climate models. But even in the past, when the climate model wasn't so detailed, they still had a lot of good results. I'm going to show you the results in the next slides. There is several institutes. So these links show all the main institutes that develop climate models. There is one in Brazil, which is the Instituto Nacional de Pesquisas Espaciais, it's INPE, and they have the BESMOA climate model, global climate model. I'm not 100% sure if it's a good one, if its accuracy. I haven't used it yet. I haven't looked into the data yet, but yeah. So I usually use Hajim. He use the ones from the U.S. China is developing very good ones nowadays. France has good uh, climate models. So, for example, in 1975, Wally Brocker, which is one of the first people that developed these climate models, he predicted that the temperature of the world would increase like this, which wasn't so far off. I mean, he predicted this 50 years ago, so he did reasonably well. And then Hansen in 1981 predicted that the overall temperature will increase like this, which is a bit better than the first estimates. And then Hansen predicts another prediction, which is also good. And now the IPCC, they look into these researchers, into this research, the main people developing a proposal for energy for the increase in temperature in the future. Of course, there are several variables. There is the variable of CO2 emissions. There are the variable of land use, which changes the temperature of the climate. Also, there's variables of the melt of glaciers, sea ice in the Arctic, rain patterns, El Nino, La Nina. For example, this 2010 probably a very strong La Nina, which reduces the temperature overall of the Earth, of the atmosphere. And then 2016, you had a strong El Nino, which also contributes to increase the temperature, overall temperature of the Earth. So several models show that yes, temperatures are increasing, CO2 emissions are increasing, and this is just to show that yes, there is climate change, there is global warming. These are the main climate models. You have some take into account aerosols in the atmosphere, uh, land, carbon, ocean aspects. So different models focus in different aspects. Some of them take a long, long time to converge. They have very high resolution. There was even a project that tried to get several people to so thousands and thousands of people gave their computational capacity in order to help process and program this data. So several people decentralize computing effort. So it requires a lot of computational speed and a lot of money, and they're very complex, these climate models. But they're getting much better every year. So several other models with aspects, atmospheric aspects, ocean, land surface, sea ice, coupling, biosphere, ice sheets, sediments, and weathering. And also, I'm sharing here the link where you can download probably 70% of all the results from these climate models. So Natalia has already gone through some of the models. She takes the prediction of wind speed, monthly average wind speed in Brazil, several regions, several locations. They have data with 50 kilometers resolution. It depends on the model. Some models, if you download the data, it's like 9 gigabytes, so very heavy data. So with this data, you have temperature predictions in different pixels, different coordinates in the world. You want to see if you want to build a house in a mountain, you want to make sure that you're building in a location that's not going to become very hot in the future. You can download this data. You can create a line showing what's the temperature, what's the humidity, how much is going to rain, wind power. So, for example, if you're developing a wind turbine in the future, you want to build a wind turbine, and this wind turbine is going to be generated for 20, 30 years. You want to know if you're building in the right place, because in 10 years the climate is going to be different, and that's going to impact the generation of wind power in your turbines. You can use this data. It's not very complicated. If you guys are interested to learn, I taught Natalia in an hour. But I don't know. Natalia is a very good student, so she learned very quickly. But I mean, it could take more than an hour, but it's not so complicated. So I'm available if you guys wanna go through in more details on these climate models. We're not gonna develop climate models. We're just using the results, right? So that's all. So now going more detail on message. Do you guys have any questions so far? So I just talked a little bit about integrated assessment models. Okay, no questions. I'm not looking at the chat, so I'm sorry if you wrote something in the chat. Just let me know. So Message IX. What's Message IX? Message is a tool that's transparent. It's open source, so you can download all the equations. You can download all the tools. It's free. It's open. You can change the code if you want. You can create your own integrated assessment models using Message as a base. It's a web interface, so you have some tools also in order to um, present your results in the internet if you want. Yasa would be very happy to share your results, maybe if they accept it, of course. Uh, Flexibility. So why flexibility? Because it can be either be used with Python or R programming. It can run with R also. So if you know how to program in Python or R, it works. The Python formulations are not very complicated, so it's Natalia is going to go through this tomorrow with you. It's just going to go through some tutorials. So these tutorials, they are very simple to understand, and then you see while you're running the tutorial, while you're developing scenarios and models, energy models, you learn Python, and it's not very complicated. You can also use Jupyter, which is a better interface, which You can document your code, document or model easier. It uses GAMS as an optimization model. So GAMS is not free, which is a bit of an issue. But if you are going to use this and you're going to produce your thesis, master thesis, PhD thesis, I can give you the license for GAMS because YASA has several licenses which they can give, but it has to be approved, pre-approved afterwards. There is GitHub. I'm not sure if you guys heard about GitHub, which is internet-based community that is used to share experience on programming. For example, Message is an open source platform, and there are several developers. And if there are some other people developing a Message or different integrated assessment models using Message as a base, they can ask questions, they can make suggestions, they can help each other in this GitHub. It's it's a network for geeks that work on coding. So this is another explanation of how the tool works, what's involved in the tool, and the formulations of the model. They follow mainly this representation where you have the commodities, which is coal, oil, natural gas, biomass available for your country, which is the primary energy. Uh, Coal, oil, and natural gas are primary energy sources, which is limited. So you have a limited amount of coal under the ground, and if you extract all the coal, you'll have no more coal. So the model takes into account also these um, restricted minerals, materials, natural resources that you have, and you will know how much coal we can burn for the next, let's say, 50 years. So the model would not propose a coal solution if it doesn't have, for example, a supplier from another country. So if you can import coal from another country, or if you cannot extract coal from its own country. But of course, you have to create this model. You have to tell the model to do this. So we're gonna go in more detail in the tutorials how to do this. A biomass also, it's limited how much land you have. Solar radiation, it depends on the quality of solar radiation. Of course, every country is able to produce electricity just with solar energy, but some countries are better than others. Rain, you have wind, and then so these are primary energy sources. And then you need a refinery, you need a hydroelectric plant, you need a solar power plant, you need a wind power plant in order to generate electricity. So you turn this primary energy into secondary energy, and then the secondary energy has to be distributed by a transmission line. So this is the energy before the transmission line. You need to have transmission lines and pipelines in order to distribute and transport the energy, electricity, or for example, gasoline, petrol, diesel. And then this electricity arrives the final customer, which you need distribution lines to reach the house. Here, the distribution line is not represented. So here is the electricity in the local house. But then what you're going to do with the electricity also depends on technology. For example, you can provide light with a LED lamp or an incandescent lamp. If you use a LED lamp, you need 90% less electricity than an incandescent lamp to produce the same service, which is electricity, which is light. Sorry. So the energy used is light, heat, mechanical power, mechanical force, which is, for example, for transportation. So this final energy depends on how efficient your technology is, how much energy you lost with transmission, and you have to pay all these technologies in order to have energy services. Of course, nowadays we have solar panels, solar power. So the solar power will arrive directly in this energy final. You would not need transmission lines, for example. Maybe you might need transmission lines if your city has too much electricity and you need to transmit to another city. But then this starts to become a bit more complicated to model in these uh, country-wide system models. Maybe it might be make more sense to use another model, not linear programming, not integrated assessment models. Maybe you want to use a dispatch model, which is, for example, energy plan, which Natalia is going to use, hopefully, or Plexus. There are several other dispatch models which are more focused on this. This is more for investing for the next 50 years, 100 years. How are you going to make investments today in order to develop your grid for 20, 30, 50 years? And in the model, you have each technology. So you have several technologies, and the technology has inputs and outputs. So that's the way you structure your overall message model. So, for example, in wind turbine, you have the primary energy is wind. So the commodity that goes in is wind. You have an input. You can give a value of one. One wind is equal to for example, 1 megawatt hour of electricity. In message, they usually use gigawatt year. So it assumes that the plant is generating 1 gigawatt average per year. So it might generate more during sometimes, less during sometimes, but the average is 1 gigawatt in the year. Um, so this is the secondary energy, which is the electricity that comes out before the grid. It still needs to be transmitted. So this electricity will then go into transmission lines to reach the demand. For wind, for example, there are several technologies. Some of the technologies have grade one, grade two, grade three. The grade ones are the ones with the cheapest costs. So, for example, wind power in the northeast of Brazil is very cheap. So you can have wind grade one, but it's limited how much capacity you can generate with this grade one, because the locations you have with good wind, they start reducing because you're already using the cheapest ones. So then it reaches a point that you have to invest in wind power, which is not as good as these locations. This is very used in hydropower generation. For example, Eletronorte developed this hydropower development plan in Brazil, and they have these stairs for each of the hydropower projects that are planned to be built. So of course the cheapest ones has have already been built, and we are using the electricity they produce. And the more expensive ones, they are being built slowly, and they have plans for the future to build new hydroelectric power plants. Of course, it's not only the costs that matter. It matters also if you're going to impact a national park, if you have people living there. Um, but you can turn the cost of moving the people, of paying the people to go. Of course, a lot of money you should pay, or paying for the environmental impacts. This can also be given a cost, and then the hydroelectric power plant will be in the planning stage, but very much in the end and very expensive. It will probably never be built because now we have solar power, which is very cheap, wind power, which is very cheap. But you can model all this in message. So the main objective function of this linear program is to reduce the cost. So you want to produce electricity and supply the demand that you have with the least cost as possible. And if you want to take into account, for example, environmental impacts, you can either give a cost to the environmental impacts that you have, or you can create a restriction. So you say, oh, if a hydropower plant has a flooded area higher than 1,000 kilometers square, we are not gonna build. So then this is a restriction that you can put in the model, for example, and then it's not going to build the hydropower plant which is bigger than that flooded area. And you can give, for example, characteristics for each of the technologies, for each of the hydropower plants that you have, and the characteristic you put flooded area, and then you have a restriction. Let's say flooded area higher than this area is not considered. So you can model this. It's not very complicated. So the main notations are the country, where the country city can be, you can make a model for your house. You can make a model for your company. If you work in a company, you consume a lot of energy. You can produce your own electricity, and you can use message to model this for the next 20, 30 years. Years, how many years you have in the horizon. So every year you want to know how much you should invest, or every 10 years, which commodity, coal, gas, electricity, which level, so primary energy, secondary energy, the grade. So this is important to tell you, just for you to have a better understanding of how the model works. It's very complicated in the first glance, first time you explain. To have perfect understanding of how this model works, it takes a lot of time. You have to work, you have to go through the tutorials, and then you start understanding the technologies that you have subiennial time steps, so you can model, for example, hours and months and days, and all the technologies will have to obey the same rules for the hours and days. So for example, if you want to supply all the demand with solar energy, in the end is going to be, the solution will not arrive. You won't have a solution because you don't have solar power during the night, sorry, and then you can supply the demand during the night. So that's misconception. It's, I forgot the technical name, um, that the model says. It says that it can't converge. So the optimization model cannot come up with a solution because it doesn't have, the model is not structured in a way that can give a feasible solution. Then you give an error. You have to understand the error, which usually is not so complicated to understand. They will say demand not met at subiennial time step zero, which is midnight, for example. And then you have to think, oh, yeah, of course, I just put solar power. I need to give more options to generate electricity at night. Maybe a battery, maybe a gas turbine, maybe a hydropower plant. So the mode is the type of, so mode is a technology, has different modes. For example, gas power plants can be combined cycle and can produce heat, can produce electricity, or can produce heat and electricity. And the mode will change according to how the power plant is operating. It can operate in three modes. So these are mode: CO2 emissions, sulfate emissions, NOx emissions, particle emissions, several types of emissions that you put in your model. And then if you run a gas power plant, you will know how much it emits because you dictate. You said, if you generate 1 megawatt hour with a gas power plant, you emit this amount of CO2. So you can also have restrictions to say, I want to emit less than, let's say, 200 kilograms of CO2 per megawatt hour. And then you will have to find the best technologies, which is the cheapest to provide electricity with this restriction. For example, a coal power plant emits 800 kilograms per megawatt hour of CO2 into the atmosphere. Nuclear power 20, solar power maybe 50 because it takes some CO2 in order to produce the solar panels, to transport the solar panels. Of course, this will depend on how the solar panels are produced. If they're produced with renewable energies, if they're produced with, and all these you can model all the whole cycle, yeah, full cycle, life cycle of the technologies. You can model also, but it's more complicated. It takes more time, so it's just better to assume the emission for solar power, so solar panels is 50 grams of CO2 per megawatt hour, which makes life easier. You don't need to make huge, very complex model, which will take a long time to converge, but you can do it in message if you want. So land use, how much land you require, land types, so good agricultural land, maybe residential urban land, which is expensive. So different types of land. Non-dispatchable rating is also important. For example, a natural gas power plant has a very high dispatchable rating because you can just turn a switch and generate electricity. Solar power, it doesn't. It's not dispatchable. It just depends on how much solar energy reaches the solar panels. So each technology has a different dispatchable rating. Relations is very interesting. For example, you can create a relation with one technology and another. For example, this technology only works if this technology works, or the opposite, if this technology works, this technology doesn't work. And if you put this input, this output changes. Relation is very used for the storage representation that we developed message. I say we, but it was really Bernam. I just tested and ran the examples and gave some suggestions. But he did this computational GAMS because he knows how to model programming GAMS. I don't know how to program in GAMS, unfortunately. I just know how to program in Python. Right. So this is the overall cost variable that needs to be optimized, which is the cost, which has several variables related to the cost. For example, the land, relations might have costs, emission might have costs, variable costs, fixed costs, investment costs of the technologies, transmission lines, coal power plants, whichever technology you have to invest to develop your grid. Um, it's very important, for example, to see these notations. If you have variable costs, if you want to give a variable cost for a technology, you need to give the name of the country that this technology is in. You need to give the time where the technology was built, the subannual time step. So in at that hour of the day, the variable cost is higher or lower during this month. So this is T is subannual time steps. So oh no, sorry, T is technology. Sorry, technology. YV is the vintage year. So when the plant was built, for example, if it was built 30 years ago, the cost of variable costs is a bit higher, might be a bit higher because the technology was older. Y is the year that's operating today, so is the year of operation. M is the mode of operation, and H is the subiannual time steps. So I said T, now H is subiannual time steps. For example, each month maybe it has a different variable cost because the gas is coming from a different location. You don't need to know explain that the gas is coming from a different location. It costs more or less at different times of the year, but you can put the subiannual time steps. So during this month, the cost variable cost is different. And if you don't put all these data, the model is not going to converge. So it's very important to know all the data that you need to give for all of these variables. So link the variable cost for example, coal power plant. So a coal power plant has a variable cost. Then you put all these costs, all these links. So you need to link for the variable cost all this data in order for the model to understand where this variable cost is related. So what this variable cost is referring to. So the restrictions, as I mentioned some restrictions. You can put restrictions in extraction and availability, or for example, gas, coal, that you extract from the ground. Commodity balance, for example, this commodity balance is already within the model, which is if you have one amount of commodity coming into a technology is equal to the amount coming out, and that can't be changed according to the model that you put. So this commodity balance is just a restriction to make sure that the model works. You have technology capacity constraints. For example, you can dictate that this technology cannot increase more than 2 gigawatts per year, cannot decrease more than 2 gigawatts per year. So then the model will take that into account, because you don't want 1 year to another change your whole energy matrix, because it's gonna put a lot of people out of work. It's gonna have problems with economy problems, because you build the power plant, you want to use it. You created capacity for people to operate, to construct coal power plants. You want to build not only one. You want to build five, six. So these are all taken into account in message with this technology capacity constraints, technology operation constraints. For example, you might have one gas power plant that cannot operate 100% of the time, because if not, it's going to break, because it's not designed to operate all the time. So then you can say that it can only operate 20% of the time. So you put the capacity factor, or a limiting capacity factor of the gas power plant. New capacity, so how much capacity you can add or not. Renewable capacity requirements. So for example, you have a target that you have to have 50% of your electricity generation in your country by 2050, because you have an agreement in Paris or in some other place for the Paris Agreement. And then you can put these restrictions. I have to generate electricity with renewables 50%, and you put 50%. The model will find the best, most optimal way to produce 50% of electricity with the technologies that you have in your model. System reliability, flexibility, share constraints, activity model, total emissions constraints, total land constraints. For example, if you don't have enough land, your country is small, you have low amount of land, your total land constraint is small. Relations also are restrictions. Relations are a bit more complex. As I mentioned, you can use message on a global scale for example, estimating a world liquefied natural gas industry. So you develop your own liquefied natural gas industry. Regional model, you can produce a renewable generation in Europe. For example, you want to see how solar and wind is going to increase in Europe. National model in Brazil, you want to make a case study for the development of wind power and hydropower. So wind power in the northeast, hydropower in the Amazon basin. Sectorial analysis, for example, electricity demand for electric vehicles. So maybe you want to have in your house, you want to buy an electric car, you want to have solar panels, and you want to charge the battery with solar panels, and you want to use the battery in your car to supply you with electricity for your demands. You can also use message for that. It might be the case that it's not the best tool to do this, because there are tools that you can do this already much easier, because all the infrastructure is ready. But if you want to do in message, you can do it. It's just going to take you a lot of time to do it. Maybe you can do it in message and make it available for in cost and charge people to use your tool. You develop the message can do this and can be a very good solution option for this. And you develop your software for home energy management, for example, you can do that. So for businesses, for example, you work in Vale, Petrobras, you want to reduce the costs of electricity on the company, you can also use message. These are the message regions. So North America, Canada, US. South America is Latin America. So LAC is Latin America. You have Western Europe, Eastern Europe, the Soviet Union, so the countries that were part of the Soviet Union, China and Mongolia, and some Taiwan and some other countries. These are countries from Pacific. So Indonesia, there's Taiwan, no, Thailand, Myanmar, some islands here. There is Australia and Japan because Australia and Japan have a similar economic profile and is close to China, so they have similar economic characteristics. So they put in the same region. South Saharan Africa, the countries from the Middle East. These are the 11 regions in Message. Message is a open source platform, so there are several people that develop tools in order to make Message more user friendly. So, for example, if you have your scenario and you load into Python code, and then it gives you, for example, this Sankey diagram, which gives you, for example, crude oil. So, how much of this crude oil is produced, how much is consumed, where it's consumed, for transport, for industry, for residential sector, thermal heating. So electricity, this is used for electricity in industry, which comes from biomass. Uh, this is hydropower. So hydroelectric, renewable hydro goes mostly for electricity also. In industry, residential sector, so there are also different sectors where this electricity is consumed. There is also the other approaches to create and show and plot and understand the model. So this is also another approach that you can look and see. I don't have the code for this one. I wasn't given, but I can look for in order to improve the presentation and for people to understand how the model works. So this is a representation which is a drawing, is much easier to follow, but it's difficult to plot this and take some time. So these type of plots it can be done automatically and save space, and you can view a very complicated, complex matrix of a model. This is more or less how a linear program works, and yeah, there might be several tools in order to make it better than this to see, but this is one of the ways that you can analyze your model. So now talking about the results for message, for example, IPCC is the International Panel for Climate Change, and the IPCC asked EASA to create the 1.5 report for IPCC. And so EASA created, they first had to estimate the amount of CO2 emissions required to meet this 1.5 degrees. And this is the amount of emissions. Nowadays, we are something around 40 billion tons of CO2 per year. So in order to reach 1.5 degrees, we will have to rapidly reach a path of rapid reduction of CO2 emissions somewhere around the end, somewhere between 2020 2030. So now we need to rapidly reduce CO2 emissions and then reach negative emissions by somewhere around 2050, 2060, 2070. If not, the world will warm up more than 1.5 degrees. There's another scenario which it would take longer to reduce CO2 emissions. So, for example, from 2030 to 2040, emissions reduce, but then you have to go negative emissions even more. So you need to increase the negative emissions in the future. So these are the inputs. So these are the restrictions. For each of these years, this amount of CO2 that you can emit. And these restrictions by every horizon, which is 2010, 2020, 2030, goes into message and they just press a button because the message global message is ready. You just add some more restrictions and then you have the results. I'm going to show you the results in the next slide. This is another type of results which is linked with the sustainable development goals of the UN, and it tries to show how energy supply, energy demand, and land impacts the several sustainable um, sustainable development goals. So, for example, energy supply. This is the this is the sustainable development goal for energy. It has a lot of synergies. It has no trade-offs. Why? Because you're looking at the energy supply. You don't need to have any trade-off in order to provide the energy supply because you're talking about energy supply. Trade-off is like, for example, I'm going to have to reduce my quality of life in order to be more efficient in my energy needs. So this is one trade-off, for example. So, for example, so for some reason you have trade-offs with food, hunger. So in order to invest a lot of money in your sustainable development and produce electricity with solar power, you have to reduce the amount of food. Maybe because you need diesel, you need gasoline in order to produce food, and this consumes a lot of electricity. And in order to be able to provide sustainable energies, you can't burn fuel and diesel. So it's very complicated issue, right? So you talk about people eating, right? So you're not going to. You have to think. You have to put in a balance. In a balance, if you want to focus on people's life quality, or if you want to focus on reducing CO2 emissions. Of course, everyone has to agree. If not, there might be a war. People will riot in the streets, and it's a very complicated issue. So these are the sustainable energy goals, and these are the results from the IPCC reports. For example, in the sustainable development scenario, SSP1, you have energy integrity, people development, economic convergence. So it's the ideal scenario where everyone goes sustainable, and the energy supply, for example, reduces a lot of the fossil fuels. So fossil fuels reduce very rapidly, increases biomass. You have increase in wind power. You have increase in solar power. You have nuclear power stays the same. You have hydropower increasing a little bit, and you also have fossil fuels with carbon capture storage. By 2050, they estimate that fossil fuels with carbon capture storage will reach the maximum, will reach the peak. And this carbon capture storage is probably also with biomass because they have negative emissions. In order to reach negative emissions, they need to plant a lot of trees, burn them, and store the CO2 under the ground back where it came from. Uh, the other one is SSP2, which is kind of the middle of the way, kind of the developments that we expect to happen. And also we have substantial reduction in fossil fuels emissions, but however the energy generation increases. So if you see the SSP1, the amount of energy that people consume stays flat, even reduces. So people reduce the energy consumption. In the SSP2, consumption increases, so people consume, but they consume more sustainably. And you have fossil fuels with CCS also. You have biomass, a lot of biomass. This biomass is probably with CCS also to produce the required negative emissions. So this was a 1.5 IPCC report, which Gaza is very proud of because it's resulted in several news feeds, citation, publications, and it's kind of the most important document for climate change. So IPCC reports, they're the most important, relevant document for climate change in the earth. So this is the other results. For example, if you can publish a paper with message results, and Lucena, which is in the Programa de Planejamento Energético da COP, which worked with Roberto Scheffer. He, for example, developed Message Brazil, and he compares with EPA, GCAM, which is the one that I talked in the beginning, Pulse, Phoenix, and Time. And then they give different results. Of course, they tried to make the model as similar as possible, but given some of the limitations, some model aspects, not every model is the same. Some are optimization models, some scenario models. So they're not the same. They give different results. Of course, not 100% different results, but some are substantially different. And he published this paper comparing different graded assessment models. You can have a look in more detail if you want to go through this path. Uh, for example, other global developments, there is India. India is using Message. They developed a tool that you can present your results better. You can change the restrictions much easier with a graphical user interface. So, for example, if you want to increase electric vehicle penetration, if you want to change gas vehicle penetration, you change this with a graphical user interface, and then you submit. GAMS creates a solution, finds the results, and then plots the results. And then you can see, for example, for the next 2020, they will invest in solar power. They will have to invest in wind, and then 2030 they will invest very heavily in coal, and 2035 also in coal. And this is a more sustainable scenario, which reduces the amount of coal investment, reduces the energy consumption, increases wind power generation. So the model that they developed shows that coal is the best solutions because I mean in India there's more than 1 billion people there, and they're very poor, and coal is cheap, and you might as well burn some coal. So now is the last part. I'm gonna talk a little bit about the role of, oh gosh, I don't have so much time. Sorry. So the role of energy storage in integrated assessment models. I might as well talk about this in another occasion then because we have 20 minutes. I took too long to go through message. So every integrated assessment model talks about wind, solar, and then you talk about the cost of wind, how much land you use, how much natural resources, how much water consumption, and kind of everyone already knows about this. But what is lacking, and I struggle a lot to find, is how much CO2 emissions the storage technologies emit, how much land it requires, how much resources it requires. What's the efficiency? Well, we know the efficiency. Efficiency is easy, but how much water you require to use this storage technologies. That's not, I didn't even find a study that says how much water requirements for each storage technology. So these aspects of energy storage, which are very important in order to plan a whole country based development, is underway. We are working a message. We are starting to add the storage formulations in the model, and there is a lot of work to be done in integrating storage technologies into integrated assessment models. I was going to go through more details on this, but I don't have much time. But this is, for example, a very interesting area if you want to write a paper, to write your thesis, for example, is adding energy storage to integrated assessment models. The only problem is that that's not very easy task. Natalia is doing that. Natalia is very brave, but yeah, so it's very interesting, but it's not very simple. What you can do, for example, is to help the people from integrated assessment models to find these parameters. So the different parameters for the different technologies, which I'm gonna address in the next lecture because we don't have so much time. So I'm gonna ask if you guys managed to install Anaconda. Can you share with me in the sorry, window? Can you guys share with me if you managed to install? If you have any questions? So Bernardo managed to install. Conrado, Anaconda installing. Thanks, guys. This is very important for tomorrow, not today. So if you can't do it today, if you can't do it now, just do it tomorrow because on Wednesday Natalia is gonna give you gonna go through this optimization model message Wednesday. Thanks, Natalia. Installed too. Awesome. Okay, great. Integration assessment models is very, very broad, very big, very heavy, very complex subjects. I'm not sure if I managed to give you an idea about it. If you have better understanding, as I mentioned, energy storage is going to become very important in the future, and it's not already implemented in integrated assessment models fully. So this is a very important task to be done. So the lecture conclusions, we have that the main objective of integrated assessment models is to plan for sustainable development. Long-term energy models aim to reproduce a real energy system with mathematical equations, including all relevant aspects in energy planning. Message is transparent, flexible, robust, and easy to use and to collaborate a collaborative tool. Global climate models are used to support integrated assessment models for future climate impacts and projections with wind power, solar power. Energy storage will play a very important role in integrated assessment models in the future. And it's very important to remember that scenarios do not predict the future, but they allow you to analyze a variety of different possible futures. And of course, you have to choose one of them. And if you end up uh, reaching a path that you are not familiar with, that you did not intend to reach, you at least know what are the risks, what are the problems with the path that you use, that you have developed, and then you are best equipped to adapt, to change, to live with the situation that you have. So scenario, this is the important thing. You are not going to predict the future with a scenario. You will try to better understand if you have that future, what you should do or not. And you should create scenarios in the future in order to select one of the best ones. Say, oh, this is a good scenario. I wanna do this scenario. I want this scenario to become a reality. But of course, you have to work very hard in order to reach that goal, that scenario that you have finally decided to focus on, to deliver, to implement. But if you don't have, for example, a very thorough, very and very good analysis, it might be the case that you don't want to reach that. It's too difficult. You would never be able to reach something to do that. So it's that's why you do integrated assessment models. So thank you guys. I give you the your grades for the first assignment. The next assignment is the week just after Carnival. Um, so I think is the 15th. 15th. No, Carnival. Yes, the 15th is Carnival, and then the 22nd. I'm gonna check again. I'm not 100% sure, but we still have two more lectures about message. Thanks so much for participating. Please let me know if you have a question about this lecture or about the second assignment, the presentation. Some people ask me what should I present, and I said it could be either the, the research proposal. So you can make a presentation trying to sell your project as a research proposal. If you feel that you are better equipped and you have better best skills for selling a project, or you can present the results, which is the third, the last assignment, which is the report. So if you feel that you're that you're better at presenting results and presenting your work that you did, then you just present the some of the results from your proposal, from your research proposal. So it's very flexible. Just please feel free to present something. There will be one day when one of you will present. No, sorry, five of you will present one day. Five of you will present the other day. You have 15 minutes and 5 minutes of discussion. I guess that's enough for you to give a good presentation. 15 minutes. Okay, guys. Thank you so much. Let me know if you have any questions. Bye bye.
Bye, Julien.
Bye, Augusto. Thank you. Eve. Friends.